this image universe before the Big Bang, actually it would be compatible with CPT symmetry. So this was our sort of formal argument that maybe there was a copy of the universe before the Big Bang, and we got it just by extrapolating the known laws through. Now, if that was the case, you see these right-handed neutrinos, this dark matter, nobody had proposed these right-handed neutrinos to be the dark matter for a very simple reason. The way we are used to calculating the abundance of particles is by assuming everything is in thermal equilibrium, right? That determines their abundance, and then you watch what happens as the universe cools and particles fall out of equilibrium. These right-handed neutrinos, if they only couple to gravity, were never in thermal equilibrium. So how do you calculate their abundance? So people said, well, we don't know how to calculate their abundance. Let's assume they're unstable, and then we won't have to worry about it. Okay? It's literally that's what happened. If, however, they are stable, and they were never in thermal equilibrium, it turns out you can calculate their abundance in this doubled universe picture because they are created by the time evolution of the metric itself. So, so you impose the CPT symmetry, it picks a particular vacuum state. In that vacuum state, it turns out there are, the right-handed neutrinos are produced essentially as Hawking radiation from the Big Bang. So I won't go through the maths of this, just tell you that the equations are completely well defined. You can work out how many right-handed neutrinos there are, and they can be the dark matter. Now let me emphasize again that the size of the universe is this very simple function. The Big Bang was a simple zero, and we're actually extrapolating this scale factor back to negative t. And turns out in the future infinity, because we have the dark energy, this function a of t has a simple pole. So it's a very basic mathematical observation that the universe we live in came out of a simple zero and is heading to a simple pole. Okay, and as soon as I use that language, you can tell I'm talking about complex analysis. And there's something even more remarkable, which is that this scale factor of the universe with realistic matter, radiation, dark energy, or cosmological constant, this is a doubly periodic function in the complex plane whose only singularities are simple poles. And furthermore, it's periodic in imaginary time. We'll come to that a little bit later. And that implies that the real universe has a Hawking temperature, like a black hole. So I won't go into any details of this dark matter solution, just to say you can solve the dark matter problem. It's a right-handed neutrino, and there is a prediction, which is if one of these right-handed neutrinos is stable, then one of the left-handed neutrinos is exactly massless. And you can see that from this picture. You see, this diagram shows the right-handed neutrino decaying. Right-handed neutrino goes into Higgs and left-handed neutrino. If you want it to be stable, you must switch off that vertex. You switch off that vertex by imposing a symmetry on the standard model. It makes this particle stable, but it also stops the left-handed neutrino mixing with it. And that means this particular left-handed neutrino is massless. And then, wonderfully, this prediction is actually going to be tested in the next 5 years by galaxy surveys. And that's a whole different story. I'm happy to talk about it if anybody's interested. But by observing the clustering of matter in today's universe, we're actually going to get limits on the mass of the neutrino, on the sum of the masses of the neutrino, and we will be able to test this hypothesis that the lightest one is massless. Okay, so let's go back to the Big Bang. The Big Bang is, in our picture, a CPT mirror. The boundary condition at the Big Bang is just like the boundary condition at a mirror. The It's a perfectly reflecting boundary condition. So when you look back at the Big Bang, actually you're looking at yourself. Okay. You can, if you like, you can focus on one side of the universe and impose these boundary conditions, or you can think about the other side. The two are completely equivalent. And one way of saying it is that the pre-Bang universe is just the mirror image of the post-Bang universe. You're all familiar, I'm sure, with the method of images. You know, if I'm solving Maxwell's equations with a perfect mirror, I can actually impose that the tangential electric field is 0 on the mirror and so on. Or I can just say, no, I'll make a if I'm right-handed, I'll make a left-handed copy of myself behind the mirror and throw the mirror away and solve Maxwell's equations, and it gives me the right answer. So that's essentially what this picture is, that the pre-Bang universe is just a mirror image of the post-Bang universe. So it's very economical, this picture. Okay, we're not adding any new phase before the universe. We're just imposing a boundary condition consistent with the most fundamental symmetry we know in physics, which is CPT. Now I'm going to talk a little bit about path integrals and gravity, because this is where another of Hawking's seminal ideas come in. I was very fortunate to overlap with Stephen at Cambridge and spent a long time with him and slowly absorbed some of his ideas. I think my current perspective is that he didn't realize how deep his insights were. Even he didn't. Okay? He had very deep insights about gravity and quantum mechanics, but when inflation came along, he said, great, the perfect place for my ideas to really be used. But I now believe that his ideas are actually so powerful that you don't need the inflation. His ideas sort of do all the conceptual work for you. So path integrals and gravity. So here are all the laws we know of fundamental physics. Einstein's theory of gravity, Maxwell's theory, Yang-Mills, they all take the same form. Dirac's theory of particles, and then the Higgs contribution. And basically what these laws tell you is that every process in the universe is nothing but an interference, You just add up a phase, that's what this integral does, add up phases, let things interfere quantum mechanically, and every natural process can be described this way. So this is a wonderful formula. It's a very difficult formula. It's probably the most oscillatory integral you could ever imagine. It's in very high dimensions, infinite dimensions. And this phase is wildly oscillating. And nobody knows if this integral even exists mathematically. For a recent attempt to define integrals like this, we have a recent paper. But nevertheless, it's a tremendously elegant formula. And so every physics experiment can be accounted for with this formula, at least a sort of particle physics type experiment, I should say. And with, now what Hawking realized is that the same formula can be used to calculate the partition function, which is the basic object in statistical physics. So essentially this formula is a matrix element of the time evolution operator, e to the minus iht. But if t is minus I beta, then that's the matrix element of e to the minus beta h, which is the Boltzmann factor. And so you can use this formula to get the partition function. What you do is take periodic boundary conditions in imaginary time, and then you look for a saddle point to this formula, which tells you the dominant Ford geometry, and the partition function is just the exponential of the gravitational entropy. So there's this tremendously elegant connection between the entropy of a space-time and the fundamental path integral formula for the amplitudes. And so Hawking used exactly this method to get the entropy of black holes. I think that's this picture. And it turns out that if you look at a black hole, so it has some classical space-time associated with it, there's a space-time metric, and the metric for a black hole turns out to be periodic in imaginary time. And that period is exactly the inverse of the Hawking temperature. So that was realized in the 70s, and Hawking and others used this to calculate the gravitational entropy. The gravitational entropy is nothing but the action for the theory calculated over one period in imaginary time. Now, let's come back to the puzzling large-scale geometry of the cosmos. So as I mentioned earlier, the universe is incredibly simple. The geometry of the universe on large scales is just flat space. You know, Euclid, it's exactly what Euclid would have guessed. X, Y, and Z, three-dimensional flat geometry. And this is a beautiful picture by Roger Penrose. He imagines the creator creating the universe, and for some weird reason, the creator chose to make the universe in this very special geometry. Flat, homogeneous, isotropic, and that's bizarre. This fact gets well, it seems bizarre because there's so many alternative geometries, you know, for the universe. Space could take any form, could be highly curved, black holes everywhere, but it's not. So now, prior to our work, the only work on the entropy of a cosmological space-time was de Sitter space. So de Sitter space is a space-time where you have nothing except a cosmological constant. Okay, so imagine I've got the simplest form of energy, and I solve Einstein's equations. This is what I get, at least if that energy is positive. This is what you get. So it's basically a contracting three-dimensional sphere, which contracts, bounces, and re-expands. To calculate its gravitational entropy, what do? Well, you go to imaginary time. You discover that the space in imaginary time is just a four-sphere. That's the most symmetric possible space. You then write down the Einstein action. It's an Einstein-Hilbert action. You calculate it for a four-sphere. It's a trivial calculation, and here's the entropy. For the observed value of the density of the dark energy or cosmological constant, you get 3.26 times 10 to the 122. So it's a huge number, the entropy of an empty universe with dark energy. For comparison of that number, the entropy of all the radiation in our Hubble volume, or our observable patch of the universe, is about 10 to the 90. So the gravitational entropy is substantially bigger than the entropy of the usual type, just the thermal energy in photons. So it's a very big number, so it's plausible that gravitational entropy actually dominates considerations of what is the most likely universe. So this is where things stood until a year or so ago. And then we realized we could calculate this gravitational entropy for a realistic universe. So how do we do it? Well, we take the line element with the scale factor. We assume that we assume conformal symmetry, which is essentially its local scale invariance of the theory, like Maxwell's theory possesses, at the Big Bang. This means that although the universe has shrunk to a point from one perspective, from the perspective of the matter in the universe, if it's like photons, like radiation, it doesn't know about the size of the universe. The photon doesn't know the size of the universe. The photon just stretches with the expansion of the universe. But you can look at the system in a different set of variables. We're just taking out that stretching, and the photon behaves exactly as if the universe was not expanding at all. Okay, so there's a special symmetry which comes in and which is related to this analyticity of the metric. Anyhow, so we look at these equations. Here is the Friedman equation. It tells you how the scale factor of the universe evolves if you have radiation, matter. We allowed space curvature. We wanted to see how this affects the entropy, and dark energy, the cosmological constant. I've just ignored all numerical factors. Now, when you write it in this form and you think about it, you see what you want to do is study this equation in imaginary time, and then you want to calculate the entropy by integrating around a closed loop in imaginary time. So that sounds impossibly difficult until you realize this is nothing but a particle in a quartic potential, and the solution for that has been known for well over 100 years. Okay, and it's well known to have very beautiful properties. There are functions called Jacobi elliptic functions, which are the general solution of such an equation. And it was known for well over 100 years that these are periodic in imaginary time. Okay, but this was overlooked until a year ago. These analytical properties are really beautiful. So we found the exact general solution to the Einstein equations. These solutions determine the Hawking temperature and the gravitational entropy. So if you look at the real part of A of t and the imaginary part of A of t, and you plot them in the complex t plane, you find there's a fundamental domain, which is a rectangle in general, and with its opposite sides identified, and then the whole complex plane is just tiled with these rectangles. So in fact, this function lives on a torus. You identify the opposite edges of the rectangle. The function lives on a torus, and there's a non-contractible loop around this torus, which is the red curve, and the action calculated on that red curve doesn't matter on the details of the curve. It just depends on the topology of the curve, how many times it goes round. And so the action is a topological invariant, and that's the entropy of the space-time. Okay? So obviously I'm only giving you a very brief glimpse of this, but I hope you get the impression this is really very elegant stuff. And this is exactly what Hawking anticipated, except he didn't realize that the solution of this was a simple analytic function. It's periodic in imaginary time, etc. In fact, in the imaginary time picture, which is more like thermodynamics, the universe is this completely finite object. Now, I say that because we have assumed that space is finite. Okay, either it's a three-sphere, if it's positively curved, which is compact. If it is negatively curved or flat, we have put in boundary conditions which make it periodic in order just to keep our formulae finite. None of what I say depends on the details of that. So it's just like studying the system in a box. And with those, given that space is a box, essentially, then the universe in this imaginary time is just a finite object, and you can study this thing, right? And to compute anything in today's universe, what you do is you analytically continue in time. So there's this sort of static picture of the universe, and we're a sort of real-time image of it. So we recently showed that this gravitational entropy favors a homogeneous, isotropic, and spatially flat universe, and a small positive cosmological constant. So both those things are exactly in agreement with what we see today. So people are still sort of struggling to make sense of this calculation, but the maths of it is completely uncontroversial. The meaning of it is another matter. Okay, and but if you take it at face value, it says we know why the universe is so simple. It's just because it maximizes the gravitational entropy. Just like where the air in this room is uniform, right? Not because anybody had a mechanism for smearing it out. It's just because the most microstates are uniform. And that's the same for the universe. So if this explanation is right, there is no need for any mechanism to explain these properties of the universe. They're just the completely obvious ones determined by thermodynamics. So there was this nice illustration in Quantum magazine that if you were to pick a universe at random, what would it look like? And that's essentially what we're doing. Pick a universe at random, and most of them will look like ours. Now, I'm going to get on to the fluctuations. And because of time, I'm going to, let's see, have I got 10 minutes?